everyone. In this lecture, we'll prove that topology on the upper half plane with respect to hyperbolic metric is the same as the topology coming from the Euclidean metric. So to prove that thing, we'll be proving that hyperbolic circles are also Euclidean circles and the vice versa. Means the Euclidean circle is again a hyperbolic circle, but the center and the radius will be different. So let us begin. Okay. So in order to prove that the two topologies coming from the hyperbolic metric and Euclidean metric on upper half plane are equivalent, so we'll be first proving that hyperbolic circles are Euclidean circles. So first, let me define what you mean by hyperbolic circle. So we have this upper half plane. So this is set up all complex numbers such that the imaginary part of this complex number is greater than 0. And we have a hyperbolic metric in the form of Riemannian metric on this upper half plane. And from there, you'll get a distance function also. So that I will denote by dh2. So this is the hyperbolic distance function. So what do you mean by circle? Circle of radius r with center A, which belongs to this upper half plane. So what is this thing? So this is the set of all elements in upper half plane such that the hyperbolic distance from this z to A is equal to r. So this is the meaning of this hyperbolic circle. So this will call to be the hyperbolic circle. And on this upper half plane, you also have this Euclidean metric. So what is my Euclidean circle? So again, it is the same thing. So z belongs to this upper half plane. And so dE2 is the Euclidean metric. So dE2 is the Euclidean metric. On the complex, on this upper half plane. Okay, so the first claim is the following. So proposition. So hyperbolic circles are Euclidean circles. Okay, so what is the proof of this thing? So let C be a hyperbolic circle. In this upper half plane with center A and radius r. So therefore what we have, so this hyperbolic distance between Z and A is equal to r if the Z belongs to your C. Now we know the distance formula between this Z and AA. So distance between the Z and A is the hyperbolic distance. It is given to be log of mod of this z minus a bar plus mod of z minus a divided by mod of z minus a bar minus mod of z minus a. And this thing is given to be your constant r. So therefore, so what we have, so mod of z minus a bar plus mod of z minus a divided by mod of z minus a bar minus mod of z minus a. So this is equal to your r. And therefore what we have, so mod of z minus a bar is equal to your, or mod of z minus a bar divided by mod of z minus a. So this is equal to your e to the power r plus e to the power minus r divided by e to the power r minus e to the power minus r. So this is this componendo and differendo we have done. And let us take this to be f of r, say. So this f of r, so this is a constant. So this is a constant. And so this f of r is also greater than 1. So now let us take z to be equal to your x plus I y and a to be your a1 plus I a2. So from this above equation, so what you will get here, so mod of x plus iy minus this a1 minus a2 is equal to your fr times mod of this x plus iy minus a1 plus I a2. So we'll get this thing, and now you can take the square both sides. So what we have here, so mod of, yeah, square of this thing, so x minus a1 plus I times y plus a2. So we have this thing here. Okay, so that is your so x square, sorry, x minus a1 whole square plus y plus a2 whole square is square of this fr times x minus a1 square y minus a2 square. So then, so we'll have a equation something like this. So x square plus y square plus some 2gx plus 2fy plus some plus some let me write down here, h is equal to your 0. So since this f of r is greater than 1, so this the above equation, so this will represent a circle in the upper half plane, and this circle is the Euclidean circle. So here you can see the center and the radius, it will get changed. So what we have proved so far, that hyperbolic circles are Euclidean circles. And now let us prove the other way. So proposition. So Euclidean circles in the hyperbolic plane are again same as hyperbolic circles. Yeah. So here, instead of taking this upper half plane model of this hyperbolic plane, I'll take the unit test model of the hyperbolic plane. So here the computation will be easy. So that's why I'll take the unit test model of the hyperbolic plane. So I'll work with this model. So here the hyperbolic metric, so it is d square is 4 mod dz square divided by 1 minus mod z square whole square. Okay, so now let us take again let us take a circle. So let C be a circle, Euclidean circle will take. So Z belongs to your this disk such that mod of Z minus A is equal to R. So let us take the circle, be a circle in this unit disk where this A also it belongs to your this unit disk. So let us draw a picture. So this is my, say, unit disk. And we have taken taken an Euclidean circle. So this is the circle. And this is my center, Euclidean center. This is A. And this radius is your R. Okay, so now what I'll do here. So this is my center O. So join this O and A by a geodesic and extend that geodesic such that it will intersect the circle C. So I have this thing. So this will be a geodesic in the unit test, and that will be a straight line. That will be the diameter. I mean, a part of a diameter. So this geodesic, so this will intersect. So this will intersect the circle C at 2 points. So these 2 points. And yeah, also note that so this angle is also 90 degree. So this geodesic intersect the circle C orthogonally. Okay. So now let us take these 2 points of intersection to be your P and Q. So P and Q is the intersection of this geodesic, blue geodesic with the circle C. So now let us take, so we'll get a point. So let W naught be an element on the blue geodesic such that so distance between, so this is the hyperbolic distance. So distance between W naught to P is same as distance between W naught to Q. So in other words, so this W naught is the hyperbolic midpoint of the geodesic segment joining this P and Q. Yeah. So this W naught, so this will lie somewhere here. So this is my W naught. So this W naught will be the center of the hyperbolic circle. So that thing we have to prove. Okay. So now let us focus on this. So this geodesic segment joining in P and Q. So we know, so there exists an isometry. So there exists an isometry T, and in fact it belongs to your this SU11. So SU11, it acts by isometry on this unit disk. So this I have given this as an exercise earlier. So there exists an isometry T which belongs to your SU11 such that so T of W naught is equal to 0. T of this P and T of this Q lies on real axis. So this we can do. So therefore, so this Euclidean circle C, so this will be transferred to a curve, something like this. So this point, let us take it to be my T of P, and this point, let us take it to be T of Q. So this geodesic segment P and P to Q is getting transferred by isometry to this geodesic passing through this O. Okay, all right. So now what we know that, so this distance O to TP hyperbolic distance, sorry, so here we are taking this disk model, so we should have this thing. So this distances are same. So again, we have that formula earlier between this hyperbolic distance and Euclidean distance. So because this from the origin, so these two distances are same. So this will imply that the Euclidean distance from O to TP and the Euclidean distance from O to TQ is also same. Okay, so now the next thing is that, so this T of C is a curve passing through TP and TQ. So T is a Mobius transformation. T is a Mobius transformation. So just check that this T of C, so it will be again a circle. So so here note that this geodesic segment P to Q is intersecting C orthogonally. So therefore, so T of C, so T is a conformal map. So T of C, it will so it will be a curve which will intersect the geodesic joining TP and TQ orthogonally. And T is again a Mobius transformation. So T has to be a T of C has to be a circle. So T of C is a circle. So T of C, it is a circle. So that thing we have proved. And if I take any point on this T of C, so if W belongs to your T of C, so distance of this hyperbolic distance from O to W, so is again constant. So this computation also earlier we have done. So this is again constant. So we have proved that this T of C, it is a Euclidean, it is an Euclidean circle. And if I take any point W on the circle, so distance of origin to that point is again constant. So this we have seen in the last lecture. So therefore, so this will imply that T of C is also a hyperbolic circle. Okay, but what we want to prove that C is a hyperbolic circle. Now C is again equal to T inverse of DC. But here, so this T is an isometry of this unit disk. So therefore, so this T inverse is again, it is an isometry. And isometry, it takes hyperbolic circle to hyperbolic circle. So this will imply that C is a hyperbolic circle. So therefore, what we have proved that, so if C is an Euclidean circle, so C is also a hyperbolic circle. So we have proved this proposition. So now from here, one easily have this thing that topologies on the upper half plane coming from the hyperbolic metric and Euclidean metric are same. So topology on this upper half plane from Euclidean metric and hyperbolic metric are same. So how do you prove this thing? So you take this upper half plane. So this is my upper half plane. So you take any point, and now you take, so you have two topology. So tau H2, it is the, let us take it to be the topology coming from the hyperbolic metric, and tau E2 means the topology on H2 coming from Euclidean metric. So you want to prove that these two topologies are same. So in order to do that thing, so what you can do, so you take a basis element of this the of a topology. So let us take a disk. So let us take this to be a Euclidean disk. So which forms, so the collection of Euclidean disks, it forms a basis for the topology on this Euclidean topology on this upper half plane. Now if I take any point here, let us take any point B here. So now you know that so there exists again a Euclidean disk contained in this thing. And in fact, so this circle, so again it will be a hyperbolic circle. So therefore, so this, so what we have here, so inside this Euclidean disk, so there is again a hyperbolic disk. And also you can do the converse also. So if I start with a hyperbolic disk, and if I take any point here, so you can get an Euclidean disk contained in this hyperbolic disk. So from here it will easily follow that the two topologies are same. Okay, I'll stop here.